Okay, the next thing we've got to talk about for calculating chemical reactions is mole relationships. So when we talked about moles in math, I mentioned that this would be useful for helping us calculate, say, how much of a reactant that we need or what relative amounts of reactants we need. And this is another step in that exact same direction. So let's say, for instance, that I was running a reaction. And let's say, let's come up with a useful reaction here. Interesting reaction. Let's use this one from the lecture notes. Let's say we have sulfur trioxide, and I can react it with sugar, C6H12O6. And if I do that, I will get sulfuric acid, and I will get elemental carbon. Okay, so there's an interesting reaction. The first thing you guys should ask anytime you see a chemical equation, what's the first thing you guys should ask yourselves? It should pop out at you. You could classify it, maybe. Ooh, I would have a hard time classifying this. This doesn't really fit nicely into any of our categories, does it? Maybe a single displacement, the SO3 kicked out this carbon. Okay, Brooks is exactly right on. This is what I want you to do. Anytime you see a reaction, like on the exam, first thing you should say is this balanced? Is this making sense? Let's see, I've got 6 carbon atoms on the left, only 1 on the right. I'm going to need 6 carbon atoms to make that work. And let's see, I have 12 hydrogen atoms here, and I only have 2. So I'm going to need 6 of these to give me a total of 12 hydrogen atoms. That gives me 6 sulfur atoms, so I better have 6 sulfur atoms over here. And that gives me a total of 18 plus 6, or 24 oxygen atoms, which works because I've got 6 times 4 is 24 oxygen atoms. So everybody agree with me that looks balanced? Let's see, I balanced the carbons first, and then I balanced the hydrogens second. And when I balanced the hydrogens, then I discovered that I had 6 sulfur atoms on the right-hand side, and that's why I put the 6 in front of the SO3 on the left-hand side, to make sure I had the same number of sulfur atoms on both sides. Good question. This one, I probably should have waited to balance the carbon last because it could be anything, but also a good idea to do the oxygens last because it was more than one place. So it's happy to do that. Anyways, excellent. Okay, so the reason that we do this, the reason that we balance it, is because we know that atoms can't be created or destroyed in chemical reactions. We know that they always react in whole number ratios like this, and so this tells me that 6 molecules of SO3 will react with 1 molecule of C6H12O6, and will give me 6 molecules of H2SO4 and 6 molecules, or 6 atoms, I should say, of carbon. But because we don't like to work with individual atoms and molecules, we can then translate this directly to moles. We know that 6 moles of SO3 will react with 1 mole of C6H12O6 to produce 6 moles of H2SO4 and 6 moles of carbon atoms. Everybody follow me there? So again, 6 molecules of this plus 1 molecule of that can make 6 molecules of this plus 6 atoms. Or we could also say 6 batches of molecules, or 6 moles, which is a batch, plus 1 mole will react to form 6 moles plus 6 moles. 6 moles of C, 6 moles of H2SO4, 1 mole of C6H12O6, 6 moles of SO3. Everybody agrees that that's what this balanced chemical equation is saying. What I want you to see now is that each of these coefficients, the 6, the 1, it's invisible, but there's a 1 there, right? The 6 and the 6, these become new equivalencies that we can use for conversion factors. In other words, I could say, if I want 6 moles of H2SO4, I'd better start with 6 moles of SO3. For the purposes of this reaction, 6 moles of H2SO4 is functionally equivalent to 6 moles of SO3, because if I start with 6 moles of SO3, then I can get 6 moles of H2SO4. Each molecule is not 1 mole, Megan. No. Remember that 1 mole of anything is 6.022 times 10 to the 23rd of that, right? So 6 moles would be 6 times 6.022 times 10 to the 23rd molecules. But just like when we were looking at the periodic table and saying that 1 H atom equals 1 atomic mass unit, and 1 mole of H atoms weighs 1 gram, we're going to move from looking at individual atoms to batches because they'll all scale equivalently. So this reaction, this is a great question, Megan. This reaction tells me 2 things. It tells me that 6 molecules would react with 1 molecule, right? But if I had 6 batches of molecules, that would react with 1 batch of molecules. Since it scales, right, a mole is the same number no matter which thing I'm looking at. It would be like saying, well, 6 reacts with 1, 6 dozen would react with 1 dozen. And then, by the same token, 6 moles would react with 1 mole. Are you following me there, Megan? That's a good question. I don't think you were the only one that had that question. Just want to make sure that we're clear on that. So these ratios, the 6, 1, 6, and 6, could refer to individual molecules, or it could refer to batches of molecules, like moles. Are you following me there? It'll take a little bit of practice. It'll take a little bit of time. But it's just a batch. Remember, a mole is just a batch, like a dozen. Except that here we're making a gajillion cakes instead of just a couple dozen cakes. So we need a batch that's bigger than a dozen. So we're going to call it a mole. Yeah. Okay, so we've got this balanced chemical equation. And the coefficients that are out in front tell us how many of each thing get used, right? So we know that 6 molecules of SO3 will react with 1 molecule C6H12O6 to make 6 molecules of H2SO4 and 6 atoms of carbon. That's essentially what these coefficients are saying once we balanced it out. We had to balance it because if we didn't balance it, then it looked like atoms disappeared or they were created from nothing. We know that doesn't happen, so by balancing it, we were able to account for the whereabouts and the destination of each atom. Okay, all right, so we know that 6 molecules react with 1 molecule to make 6 molecules and 6 atoms. These numbers are all relative. 6 of these will react with 1 of those. And so if I had more than 6, let's say I had 6 dozen. Well, if 6 reacts with 1, then 6 dozen would react with 1 dozen because it's just relative. And if 6 makes 6, then 6 dozen would make 6 dozen. I'm not sure that I'm following, Megan, because 6 will always react with 1. And if it was 6 dozen, then it would be 6 times 12, right? And that would be 1 times 12. So that the 6 and the 1 always stays the same. And if I'm ever multiplying them with something else, like a dozen, that number always stays the same as well. It looks like it's a 3. Hang on a second. Be back up here. This is a 1, right? Should be a 1. Yes, it's a 1. It couldn't be a 3. That wouldn't make any sense. Yes, it's a 1. I was trying to, because usually when it's just a 1, we don't show anything. But I wanted to pull out the fact that this is a 1 to help us explicitly see this relationship. There we go. Okay, does it make more sense? So if 6 reacts with 1, then 6 dozen would react with 1 dozen, or 6 score would react with 1 score, or we're just going to say a mole is a different kind of a batch, so 6 moles is going to react with 1 mole. Did that clarify the issue? Yep, just looking at it in a different way. These numbers are the same numbers that we had when we balanced. We're just going to use that to identify relative relationships. For the purposes of this reaction, when it's occurring, 6 of these will always react with 1 of those. Or 6 batches will always react with 1 batch. For the purposes of this reaction, 6 of these will always make 6 of those. Or 6 batches of the SO3 will always react to make 6 batches of the H2SO4. There are other relationships we could say here. We could say if I'm making 6 batches of H2SO4, then I know I will also be making 6 batches of carbon because they are created in exactly this ratio. Or if I'm using 1 batch of my C6H12O6, then I know I'm going to get 6 of those, or 6 of those. So there's a whole bunch of relationships here between each reactant and each product that we could pull out of this equation. But we don't need all of them at the same time. We might just need 1 or 2 of them. Depending on what I give you and what I'm asking, that's what you're going to pull out. So let's say, for instance, that I have 15 moles of SO3. I'm going to react 15 moles of SO3. And I want to know how many moles of H2SO4 can I get when I run this reaction. Can you guys guess how many moles of H2SO4 you're going to get? Danny says 15. Brooke says the same thing. You guys are exactly right. If 6 moles of SO3 makes 6 moles of H2SO4, then it's perfectly logical to assume that 15 moles of SO3 is going to make 15 moles of H2SO4. Now, let's put that in dimensional analysis style because it's not always going to be as clear as that, okay? Dimensional analysis style is going to say, let's see, we're starting with 15 moles of SO3. And I want to get rid of moles of SO3, and I want to be left with moles of H2SO4. So yes, this is a big equation with lots of things in it, but really for the moment, I'm looking at this and I'm looking at that. I'm looking at the relationship between the two. That 6 of this makes 6 of that. So that's what I'm going to put here. 6 moles of SO3, I'm going to put that on the bottom because that's what I want to cancel out. That's going to make 6 moles of H2SO4. So my moles of SO3 will cancel out. And if I multiply that through, I should get the answer of 15 moles H2SO4. Okay. Do you guys see what I just did there? This is kind of the crux of the matter. I used the coefficient of my balanced equation as a conversion factor. Travis is with me. Anybody else? Excellent. Excellent. Because we're running low on time. It's going to take us. Let's look at our in-class activity sheet here. So section 4, going to consider the following reactions. Here we've got reaction A, B, and C. We can say. And then I'm going to have you, I'm asking some questions about each of these. The first thing that you should do before answering these questions is what? Again, in the margins, we need to balance these because if we don't have balanced equations, then we're not going to have the right coefficients of our balanced equations to use as conversion factors. So balancing is vital. So let's say PCl3, I've got 3 chlorines. I'm going to need 3 chlorines, 1 phosphorus. I have 3 phosphoruses. 2 hydrogens everywhere. Let's see, 1 oxygen, 3 oxygens. So I'm going to put a 3 here. That gives me 6 hydrogens. And I have 6 hydrogens. Everybody agree that looks balanced? Yes. Okay. And just for the purposes of following this here, I'm going to put a 1 here and a 1 here. Because that's if it's invisible, there's just a 1. Okay. Next one, XCF2 plus water makes Xe and HF and O2. Let's see, I've got 1 xenon, 2 fluorines. I'm going to need 2 fluorines here. And, I've got 2 oxygens on the right, so I'm going to need 2 hydrogens on the left. Or sorry, 2 waters. Oh, that gives me 4 hydrogens. I better have a 4 HF to make that work, and a 2 and a 2. 2, 2, 2, 4, 1. Does that work? 2 xenons, 4 fluorines, 4 hydrogens, 2 oxygens. I think that works. Let me know if you guys don't see that. And let's see. 2 carbons, 2 carbons, 6 hydrogens, 6 hydrogens, that gives me 4, 7 oxygens minus 1, that's going to be a 3 there. Okay. Do any of these not look balanced? But that's the first step. It's important that we get it right before we move on. So let me know if I did any of those wrong. I tried to kind of rush through those so we could spend extra time on the next couple sections. Is there a particular problem, Danny? Or do you see it now? Step 4. Oh, okay. That's from last chapter, so there'll be extra practice on that. But if you want to talk to me about it in class on Wednesday, we can go over and practicing. But really, it's just a matter, the way that I do it is I'll pick an element and I'll eyeball it, left-hand side, right-hand side, make them the same number. Sometimes I have to go back and over it again if I have to change a different coefficient. But okay, let's use these coefficients and see what we can about mole-to-mole relationships. So here we go. How many moles of H3PO3, so this is what I'm looking for, could be produced by the reaction of 0.15 moles of PCl3. So mole-to-mole relationships is comparing your coefficients of the balanced equations. So in this section, we're going to use those coefficients of the balanced equations to do this. So what is my ratio of H3PO3 to PCl3 according to the coefficients of my balanced equation above? Robin and Brooks, exactly. I've got 1 PCl3 for every 1 H3PO3. So 1 mole PCl3 will react with, or for the purposes of this equation, is equivalent to 1 mole H3PO3. Pardon, not react with, but will produce. 1 mole of PCl3 will produce 1 mole of H3PO3. So if I'm starting with this, 0.15 moles PCl3, I can use this equation, this equivalency, to say 1 mole of PCl3 will give me 1 mole H3PO3. And if I do that, what's the answer to my question? How many moles could be produced? .15 moles. H3PO3. That's the answer. Okay. You're going to do the exact same thing these next two. You're going to look for the relationship between the HF and the XeF2 in my original equation. So in this case, it's going to be 4 to 2. You're going to look for the relationship between the CO2 and the C2H5OH in the original equation. Okay. So make sure that you're pulling out the right coefficients when you're answering the question, because there's extra information obviously given by these equations that you don't use when you're answering this question. Once you have those coefficients, you just set them up to cancel out what was given, and that should give you what was being asked for. Okay. I'm going to let you guys take a stab at that and bring it to class on Wednesday. I know it looks intimidating, but it really is just a one-step conversion between what I gave you and using those coefficients. Okay. Now, of course, it gets harder. That's what this next step is. That is to say, in part A, I have moles that I'm converting from moles of one thing in my equation to moles of something else. Part B is reminding us that if we have moles of anything, then we can calculate the mass of that. And that's much more convenient to use mass because, as a matter of fact, we don't have scales that measure moles, that only measure mass. So, if we have moles, then I can ask you to take an extra step and to convert from mass to moles before you do this conversion, or if you convert to moles to find out what the total mass would be. So let's do this one together. How many moles of C2H5OH would be required to produce 70 kilograms of carbon dioxide? Oh, look, Megan, I was so rude. I didn't even give you grams, I gave you kilograms like a jerk. Crap. Boo, okay. All right. So we have to ask ourselves, what do we know about the relationship between moles of C2H5O2 and carbon dioxide? Or sorry, C2H5OH. So that's going to give us this. Here's one conversion factor we're going to need to know. That 1 mole of C2H5OH will produce 2 moles of CO2. That's what our equation is telling us, right? You guys see that in the coefficients of my balance equation? You guys following me on that conversion factor? Okay, so we know this. And if we're looking at CO2 and we have mass, we need to know something about the molar mass of carbon dioxide. You guys can do that. It's going to be 1 carbon plus 2 oxygens. So that's going to be 2 times 16 is 32, plus 12 is 44. You guys don't ever have to memorize these. I've just used them for long enough that I've got a good idea. So CO2 is 44 grams per mole. That's going to get us from grams of CO2 to moles of CO2, which is great, because then I can go from moles of CO2 to moles of C2H5OH. What about kilograms? How do I go between grams and kilograms? What are we going to use there? A 1,000. There are 1,000 grams in 1 kilogram. Okay, you guys have 3 different conversion factors that you guys can use to set up this reaction, this equation to solve it. You guys can do it. You should pause it right now. If you're watching this later, you should pause it right now and try it. I'm going to do it for the students who are here. We're just out of time, but I want to give you guys at least one example of doing this. Start with what you're given, 70 kilograms CO2. Want to get rid of kilograms? Here's where that is. 1 kilogram is 1,000 grams. Excellent. Kilograms cancel. Here's my grams. 44 grams of CO2 in 1 mole of CO2. And here's where it's going to be really important to include not only your measurement units, but also your identity units. Your grams cancel, your CO2 cancels. You don't want to use the molar mass of this guy because that's not what you were given to start. If you did use the molar mass of this guy and you included it here, you would see very quickly why that was the wrong thing to use, and it would be self-correcting. But you'd have to keep including those in your units to know. All right, now we're at moles of CO2 and we want moles of C2H5OH, so we're going to plug this in here. 2 moles of CO2 for every 1 mole of C2H5OH. And if I do that, I should be left with just moles of C2H5OH. Okay. I want you guys to note this is metric conversion. You guys know from chapter 1, you memorized it forever ago. This is just your molar mass conversion that we did at the very beginning of class today. And then this finally was your mole to mole conversion that we had to use our coefficients of the balanced equation to get. So we're stacking conversions that you guys know how to do, each one individually. We're just going to stack them all up to get the answer we're looking for. And we should be almost done. I suppose we should plug the numbers in. We can do that. See if we get the same answer. 70 kilograms times 1,000 grams per kilogram divided by 44 grams per mole divided by 2 moles. It's going to give me a total of 795 moles of C2H5OH. All right, I'm going to stop this recording now because we are out of time.